Okay, so I've copied down the relevant information from the problem that we are in the middle of. We're trying to calculate this flux integral. That's sometimes called, by the way, the surface integral of f across s. It's also called a flux integral. Okay. So this was our vector field. We had parametrized, remember, the top part of the sphere. I forgot to write down. Theta is varying from 0 to 2 pi, and phi is varying from 0 to pi over 2. So the region that we're integrating over in the theta phi plane is this rectangle right here. We'll call that D. Okay, so we used this parametrization. When we calculated the cross product of the partials, we determined that that was pointing inward. And we determined that by just picking a point. A convenient point to pick was the frontmost point on the sphere. And we saw that this vector, without the negative sign in front, was pointing inward. We wanted outward, so we took the opposite of that vector. Okay, I do want to see that work, by the way. You might remember, I remember because I've used this parametrization so often. I remember that this parametrization gives me an orientation that's pointing inward. So that if I use this parametrization, I've got to take the opposite of the cross product. But I don't want you to just memorize that. So I do want to see if you're picking a parametrization and then having to figure out whether the orientation works. I want to see you picking a point and checking that. So do show that work. Okay, so then this is what we got. This is our outward normal vector. And this is what I like to call the non-normalized normal vector. I didn't bother to normalize it by dividing by its magnitude. That's because when I go to write this, it's going to become the double integral over D, this region in my parameter plane. Now, I'm going to write f in terms of my parametrization. So z was 2 cosine phi. So I'm going to be writing 2 cosine phi, comma 2 cosine phi, comma 2 cosine phi. That's my very exciting vector field f. I'm going to dot that with this vector right here, 4 sine squared phi cosine theta, 4 sine squared, I did not mean sine squared 4, I meant sine squared phi. Sine squared phi sine theta, 4 sine phi cosine phi, and then we'll integrate that dA. What's happening is n would be this vector divided by its magnitude. But ds is the magnitude of this vector times dA. The magnitude that I get as my scaling factor cancels with the magnitude that I would get in normalizing this. Okay, so just like with a work integral, I'm not integrating vectors, I'm integrating a real valued function. So I have to just work out the dot product before I'm ready to integrate. So this is going to equal the double integral over D of, let's see, we're going to get 8 sine squared phi cosine theta plus 8 sine squared phi cosine sine theta plus 8 sine phi cosine squared phi dA. All right, now I'm integrating over this rectangle in the theta phi plane. Usually I integrate with respect to phi first and then theta because I'm just used to doing theta last. In this case, however, I am going to integrate with respect to theta first. And that's just some strategy. I'm noticing that here, I'm going to end up integrating cosine from 0 to 2 pi. I'm going to get 0, that term's going to go away. I'm going to end up integrating sine from 0 to 2 pi. That piece is going to go to 0, it's going to go away. So that all I'm going to have to integrate with respect to phi is this piece. So you want to sort of be on the lookout for things like that. If you don't notice it, it's not the end of the world. It's just going to take you a little bit longer to integrate. But that's a neat strategy to notice if you do. So I'm going to switch to an iterated integral. So I'm going to do 0 to pi over 2 as my outside. 0 to 2 pi. Whoops. Some video editing has taken place. What happened is when I first shot the video, I had the problem written at the bottom of the board. I'd run out of space. I recopied it to the top of the board and I miscopied it. I initially copied this last term as 8 sine squared phi times cosine squared phi. Now that's a much more involved integral. Of course, with even powers of sine and cosine, we would use the double angle formula for cosine to evaluate that. But this one is actually a much nicer one. We'll be able to evaluate that with just a simple u sub. Okay, so as we evaluate this, my shell is this integral from 0 to pi over 2 that we're going to do with respect to phi. What I'm going to do is just integrate each of these terms with respect to theta. And I think I'm going to go ahead and for each term write my evaluation bar, just so I remember that I'm plugging in for theta. So for this first term, all the phi stuff is constant. So we're getting 8 sine squared phi cosine phi times an antiderivative of cosine of theta would simply be sine of theta, and that's evaluated between 0 and 2 pi. Plus, for this next piece, again, the phi parts are constant, so 8 sine squared phi cosine phi, and then an antiderivative of sine of theta would be negative cosine theta. I'm just going to change this to a minus sign, and then a cosine of theta, and that's evaluated between 2 pi and 0. And then for this piece, there are no thetas in here at all, so all of this is constant. And I know that when I integrate a constant, I get that constant, so 8 sine phi cosine squared phi, times the length of, in this case, the theta interval over which we're working. We were integrating from 0 to 2 pi, so the length of that interval is just 2 pi. Now, when I go to evaluate this first piece, of course, sine of 2 pi and sine of 0 are the same, so that first piece is 0. Same thing happens here. Cosine of 2 pi and cosine of 0 are the same, so that second piece is 0. So what we're left with is just the integral from 0 to pi over 2. I think I'm going to go ahead and factor out the 8 and the 2 pi. So that's going to be 16 pi. And then on the inside, we've got sine phi times cosine squared phi d phi. Now that we can do with a u sub. Let's let u equal cosine phi. So du is negative sine phi d phi. Looks like we're going to need to have a negative sign, which will counterbalance with another negative on the outside. Okay. So negative 16 pi, the integral from the u value at 0 is cosine of 0, that's 1. To the u value at pi over 2 is cosine of pi over 2, that's 0. And then this is just u squared du. So that's negative 16 pi, u cubed over 3, evaluated between 0 and 1. Do be careful. You could have, if you wanted to, used that negative sign to switch the limits of integration to be going from 0 to 1. I kept it there, so 0 is my upper limit of integration. So this is 16 pi times what I get is 0. At 0 is 0 minus what I get at 1 is 1/3. I'm sorry. It's negative 16 pi times 0 minus 1/3. Now those two negatives cancel, and so we get 16 pi over 3.